Hi folks, so let's continue our journey on circles. Today we will be looking at arcs, right? We spent some time looking at properties of chords, equal chords, chords being equidistant, chords subtending the same angle at the center, right? All of that, we are done with those. And now let's focus all on arcs, okay? So before we jump into the theorems, let's have a recap on what an arc is. An arc is just a part of the circumference, right guys? So in this case, let's say we have AB. AB is an arc. If the central angle is 90 degrees, then we call this portion, the sector, right, as a quadrant. Am I right? If the central angle is a 180 degree, then we call that sector a semicircle. So all this is something we have studied early on. And what we also saw that if we have concentric circles like this, definitely if this were an arc UV and I extended this line, then you'll observe that, sorry, it's not a perfect straight line, but I hope you get the point. If you have SU and TV are the arcs of the smaller and bigger circle respectively, what you'll observe here is the fact that this central angle is the same. It could be a 60 degrees, it could be theta, it could be anything. So the central angle is the same, in which case you can actually say that the arc lengths US and the arc lengths TV are proportional. Proportional to what? To the radius or the circumference of these concentric circles. I think this is something we discussed in detail. I just want you to have this at the back of your mind when we're studying about theorems on arcs. Okay. A quick recap on what a segment actually is, right? A segment comes into being because of a chord. The minute you have a chord, the area bounded or bound between a chord and its corresponding arc. This area is a segment, but as you can see, a chord splits the circle into two areas, right? The one that is smaller, whichever arc is smaller, the area bound between the minor arc and the chord is called the minor segment, whereas the area between the major arc and the chord is the major segment. Right, guys? Okay. So in this case, what we have is a major segment of the chord AB. Fantastic. Let's quickly correlate the circumference of the circle and the arc length, right? Now, in this case, I have a complete circle. The circumference, as you all know, is 2 pi r. Supposing I now split the circle into two equal parts, what happens to the circumference, folks? So let's say these A and B are the points. The circumference of the arc AB is now pi r, or what did we do? We just divided the circumference by 2, so we got pi r. Am I right? Okay. Now let's continue further. Let's say we now have the arc CD. It subtends an angle 90 degree at the center. So you know that this is 1/4 of the circumference, right? The arc length CD. I'm putting it like this to indicate arc length and not the chord. The arc length CD is actually equal to 1/4 the circumference. Why is that? Because I split the circle into 4 equal parts. So obviously, even my circumference should be split into 4 equal parts, right, guys? So this becomes half pi r. Am I right? Okay. Now, pause for a minute here and let this be a totally different arc. Let's call it PQ. Now this time we don't know the angle, we're just calling it theta, right? Now look at this in a different way. The angle about a point, the angle about a point is 360 degrees. Am I right? In case 1, this is case 1. In case 2, the angle of this arc, the central angle of this arc is a 180 degree, okay? In case 3, hang in there, in case 3, the angle is a 90 degree. And in case 4, let's see what if we have any angle, a generic angle, theta. So here, if the central angle or the angle of the arc, in this case, the arc happens to be the complete circumference, right? That's also an arc. Let's say I start at a point R and I finish one complete circle and I come back at R. That's also an arc. So if it's 360 degree, it's 2 pi R. If it's 180, it's pi R, right? If it's 90, it's a half pi R. Do you see what's happening here? Do you realize that the arc length, guys, the arc length is indeed a function of the central angle, or it depends on the central angle, okay? Or it is proportional to the central angle. Observe carefully here. Now, if you look at how did you get pi r, if you actually say this arc AB, the length is 180 by 360 times 2 pi r, and that is how, okay, you got this gets cancelled, this is twice, and hence you end up with pi r, right? So the arc length AB is 180 by 360 times 2 pi r. The arc length CD is 90 by 360 times 2 pi r. Which you will definitely end up with a half pi r, okay? Therefore, if I have an arc PQ, then the arc length of this is going to be theta by 360 times 2 pi r, okay? So it's just an obvious conclusion. So all you need to remember is that if you know that the central angle of an arc is theta, okay, then its arc length is given by theta by 360 into the circumference 2 pi r. Okay, guys, isn't this, a very logical way to arrive at the arc length? Well, you don't have arc length in grade 9, but when we talk about arc and the angles, central angles of arc, it's just interesting to observe these properties, and they come quite naturally. Okay, so this is the first observation, arc length. If you know the central angle, you can always find the arc length. Okay, cool. Now, let's also spend a few minutes on the perimeter of a sector. What's a sector, folks? It's an area bound between, let's quickly recap. Supposing I have an arc PQ, then if I join the endpoints of the arc to the center, the area bound between the arc and its corresponding radii is a sector. This is a minor sector and this is a major sector. I'm sure you guys know this. Okay, cool. So let's look at the perimeter of a sector. Now, if the entire circle is a sector, which it is, right? Then you know the perimeter. But let's look at this sector, the sector AB, this complete portion that is marked in red. Then what could its perimeter be? Now, perimeter of any sector, guys, pay attention, is a sum of the arc length, right? You look at the arc AB here, the arc goes like this. You take this length and you add the diameter, or twice the radius. So always the perimeter of a sector is L, where L is the arc length, and twice the radius, okay? If you have a quadrant, it's the same story happening there. Let's take CD like last time. If you have a random arc whose central angle is theta, then we know the arc length. All we need to do now is let's find out the perimeter of this sector. The arc length, you know, guys, is the central angle 180 by 360 into 2 pi r is my L. To this you add, so the perimeter, to this you add, this becomes 1 by 2 and pi r, you know all of that. To this you add 2r, right? In this case, it is a 90 by 360 into 2 pi r is the arc length. To this, which becomes what? Half pi r, am I right, folks? 4 times here and a 2 times there, half pi r plus 2r. It is this that you're adding to find the perimeter of a sector. Similarly, if you have an arc whose central angle is theta, theta by 360 times 2 pi r is my arc length. To this, I'm going to add a 2r, right? Then it's all algebra, folks. 2r is common. What are you left with? You're left with theta by 360 into pi, right? Because 2r is what is taken common out, plus, oops, the butterfly is here. So let me write it above. It's 2r plus 1. I've just simplified it. You don't have to remember this formula because, I just want to tell you that if you know the central angle, you can find out so much about the arc. You can find the arc length, you can find the perimeter of the sector, and obviously the area of the sector, right, guys? The area of a circle is pi r squared. The area of a semicircle is pi r squared by 2. The area of a quadrant is pi r squared by 4. Right? What about the area of a sector? Because bear in mind, the quadrant or the semicircle are sectors by themselves. So let's go back to our favorite scenario, PQ, where you know the central angle theta. What can you say about the area of a sector whose central angle is theta? Something tells you, well, it should still be proportional to the angle that it sweeps. So it is theta by 360 times pi r squared. How did we get that? I'll just quickly apply the same logic here. You obtained pi r squared by 2. If you look at it in a different way, the central angle of a semicircle is 180 degree by 360, which is the complete angle around the point. It is this times pi r squared. And that's how you got pi r squared by 2. Am I right? Same thing here. The angle swept by this arc, okay, CD, which forms a quadrant, is 90. So the area of the sector should be a slice of this entire circle. That slice or the portion that we're talking about is what is defined by the central angle. So it's 90 by 360 into pi r squared, and that's how you got a 1 by 4 pi r squared. So in general, if the angle is theta of a sector, the central angle of a sector is theta, the area of the sector is given by the formula theta by 360 into pi r squared. Right, guys? So please make a note. The minute you know the central angle, you can find the length of the arc, the perimeter of its sector, and finally the area of its sector. So that is the significance of the angle, the central angle of an arc. Why I'm telling you all this is because we look at properties pertaining to central angle of the arc, and you might ask, well, what's the point in knowing all of these? This is the advantage of knowing the central angle. If you know the central angle, you can arrive at a lot of other things about the arc. Okay, fantastic.